Hello and welcome to our session today where we will be exploring the three essential aspects of the power system and substation. Firstly, we will dive into the structure of the medium voltage networks and substations and understanding how they function and how they connect with the grid. Next, we will move into the structure of the high voltage networks and substations, focusing on the components, layout, and key design consideration for this infrastructure. And finally, we will discuss the Substation Communication and IEC 61850, the global standard for digital communication in substation, and how it transforms the way these systems operate and communicate. Let us get started with this exciting journey into the world of electrical network and substation. As you can see from our screen here is the basic structure of the medium voltage networks and substation. So in the following chapter, we will explain an overview of the basic structure of the medium voltage substations. And as you can see we have two single line diagram for the typical medium voltage distribution substation. The typical medium voltage networks are modeled in radial distribution network and ring distribution network. So you can see the difference from the left figure on the screen representing the radial network, but the right one representing the ring network. And we will see the difference, inshallah, in the next slides. What is the difference between radial network and the ring network? So you can see from our single line diagram here the incoming feeder with the transformer. Also, we have some outgoing feeders and connected loads. And here in the ring networks, we have also the bus coupler circuit breaker. Referring to the medium voltage substation topology, here is a typical medium voltage substation structure with a double bus bar and several feeders. So you can see the number of feeders is variable. Referring to the dotted lines, we have incoming feeder with transformers 1 and 2. We have bus bar 1, bus bar 2, and we have some of the outgoing feeders plus the transverse coupler. So you can also differentiate between the disconnector here ligand or symbol and also the transverse coupler circuit breaker, which have the arc quenching medium. So the basic structure of the medium voltage outgoing feeders, as you can see on the left, here is the structure of the medium voltage feeder with the voltage transformer connected to the feeder, which called T5. So the T5 here is the voltage transformer connected to the feeder lines, and this also VT can be connected to the bus bar, as we will see. So as you can see here, the main difference between the two single line diagram is we have here the Q0, which representing circuit breaker in withdrawable circuit breaker, which is commonly used in the medium voltage structure and the medium voltage substation. So Q0 here representing the circuit breaker with the arc quenching medium. We have also T1 is the current transformer, T5 is the voltage transformer. We have Q1, which is the bus bar isolator for bus bar 1. Q2 is the bus bar isolator for bus bar 2. Q8 is the earthing isolator for the feeder. We have also the T51 and the T52, which can be connected to the bus bar directly. So here is the T51 is the voltage transformer for bus 1, and 52 is the voltage transformer for bus 2. So the structure of the medium voltage feeder with the voltage transformer connected to the bus bar also may look like this example in our screen. And also to explain what is the difference between the circuit breaker and the disconnector. So the circuit breaker with the arc quenching medium can be used to interrupt the fault current and to clear the electrical faults. So the arc quenching medium in the circuit breaker, like air or SF6 or vacuum or oil, is used to extinguish the arc when the interrupting current. So the circuit breaker can operate under both normal and fault load condition. And on the other side, the disconnector or the isolators provides a visible open point for maintenance and for safety. So there is no any arc quenching medium. So the isolator is designed for use only when no significant current is flowing, not for breaking load current. So it must be operated when the line is dead or de-energized. Also, it can be manually operated to provide a visual confirmation of the disconnection status. So in summary, the main difference between the circuit breaker and the isolator is that the circuit breaker can break the fault and the load current with the arc quenching medium, but the disconnectors isolate the circuit but cannot interrupt the load or fault current. So the circuit breaker are used for protection, and and the disconnector are used for isolation and for safety. So as you can see here is we have an on-site example from medium voltage substation, which can give you overview about the components of the medium voltage outgoing feeder. So in the figure, you can see a detailed structure of the medium voltage outgoing feeder. So you can see from here the circuit breaker, as you can, withdrawable circuit breaker. We have also the low voltage cabinet, which have the protection relays, the auxiliary relays, and miniature circuit breakers and auxiliary devices. We have also the current transformer, as you can see, and we have a withdrawable voltage transformer in the medium voltage outgoing feeder. So this example is, or this example of the medium voltage substation is air insulated medium voltage switch gear Siemens medium voltage switch gear, which can be used up to 24 kV. On the other side, we will talk now about the basic structure of the high voltage networks and substations. So you can see now in our screen the single line diagram of a typical high voltage transmission system. So the high voltage transmission system are typically strongly meshed network. Meshed networks, and here's an example structure is shown in our figure. So in short, the high voltage meshed networks provides increased reliability and redundancy. So multiple buses ensure the power delivery even if one line fails. Also, it provides you with one more advantage, which is reduce the power losses, and it's improve the efficiency compared to the radial systems. And also, the third advantage is to enhance the capacity for long distance transmission. So it's better suited for transmitting large amount of power over a long distance. So you can see from our mesh network here is the incoming feeder with a step-up transformer and generator. Also, we have the outgoing feeder with a step-down transformer or coupling transformer, for example, from 380 kV to 110 kV. We have also the substation double busbar systems, and this arrow represents the connected load or the outgoing feeder. So the basic structure of the high voltage substation or the high voltage outgoing feeder, as you can see from our screen, we have a typical high voltage double busbar substation structure with longitudinal transverse and transverse couplers. So as well as the several feeders also can be connected and can be represented here by the dotted line. So the number of feeders is a variable. We have here a circuit breaker. We have a longitudinal dash transverse coupler. We have 4 incoming feeders, 1, 2, 3, 4. We have busbar 1A, busbar 2A, busbar 1B, busbar 2B. And the main difference from the medium voltage substation is that the high voltage substation topology normally require a higher effort because it have more isolators, more transformers, grounding equipment, couplers, and more busbars. Now we will talk about the outgoing feeder topology in the high voltage system. So you can see the structure here of an example of high voltage feeder with a double bus bar can be shown in our screen. So we have the Q0 representing the circuit breaker, as we said, Q1 bus bar isolator for bus bar 1, Q2 bus bar isolator for bus bar 2. We have also T1 representing the current transformer. If we have voltage transformer, will be represented by T5, which can be used for the line, and you also in some cases you will have a VT for the bus bar, and it can be used for synchro check applications for the overhead lines. We have also the Q8 and the Q9. The Q8 is the earthing isolator for the feeder, and the Q9 is called the feeder isolator. And here's an example of the high voltage substation. So you can see the structure of the high voltage feeder with the air insulated outdoor switchgear. So you can see here the Q0 representing the circuit breaker, Q1 is the busbar isolator, and also we have the bus bars. We have the T1 for representing the current transformer, T5 representing the voltage transformer. Here is another example also for the high voltage substation, which is the structure of high voltage feeder with gas insulated outdoor switchgear. Gas insulated outdoor switchgear, which means a hybrid switchgear, AIS and GIS in the same time. And this kind of substation is normally used due to space limitations. So you can see from our example here the circuit breaker breaker, the bus bar 1, bus bar 2, the Q1 and Q2, and also the Q9 for the feeder isolator, and in addition to the current transformer represented by T1, voltage transformer represented by T5. Now we will talk about the substation communication architecture from the point of view of the IEC 61850 standard. So you can see in the process we have different levels here. So in the process level you will find the switch gear, like the circuit breaker, disconnectors, and so on. We have also the measuring device or the merging unit, which measures the analog voltage and current measurement and transfer it to digital values to be published on the bay level. So the bay level, we have a bay controller, we have a protection device, and many more IEDs. And on the station level, you will find the HMI substation controller, and we have also the control center in the SCADA level. So here is the hierarchy or the architecture of the substation communication. And here is the evolution of the substation automation and a comparison between the conventional, the hybrid, and the digital substation from the point of view of all levels. So as you can see here in the process level, in the conventional substation, we have the CT and the VT, which is a conventional instrument transformer, and the conventional switch gear. In the bay level, we have the hardwired protection and control. Okay, and in the station level, we have the HMI and control board, and the SCADA level, which is represented by the control center. On the other side of the hybrid substation, here is the process level, can be represented by a conventional instrument transformer and switchgear, and it will be by using the merging unit, it will transform this analog current and voltage measurement into digital values to be published on the bay level. And the bay level, there is a lot of protection and control intelligent electronic devices or IEDs, and connected by using the Ethernet to the HMI and the gateway in the station level, and also connected by the Ethernet to the control center, which is available in the SCADA level. Okay, last but not least, the digital substation, we have here NCT and also CVT and low power instrument transformers such as LBIT for the current using the Rogowski coil and also the voltage transformer, and we have also a merging unit to transform or can be used to transform this analog values of the current and the voltage into digital values to be published by using the Ethernet to the bay level. And we have multiple protection on the IEDs connected to the Ethernet, connected by the Ethernet to the HMI and gateway, and last but not least the SCADA level represented by the control center. So you can make a quick comparison between the digital hybrid and conventional substation. As you can see, here is the type of connection also is copper wiring, but in the digital substation is completely digital, so it will use the Ethernet connection. So here is the three main goals of the IEC 61850. So we have three main goals for this standard. We will explain it one by one. So in terms of interoperability, IEDs from different manufacturers can exchange the information and perform a combined functionality with each other. So it's representing the communication between IEDs from different vendors on the data model and services. The second main goal, which is the free configuration, the standard shall support a different philosophies, which should allow manufacturers and utilities a certain degree of freedom to support specific requirement of different systems. And last but not least, the long-term stability. So the standard must be able to follow the progress in the communication technology as well as the system requirement. So it's providing you or give you separating abstract information from the specific physical mapping. So from the explanation above, we can conclude that the effort must be done to get interoperability between different devices instead of plug and play process. It is necessary to provide this effort to get interoperability between different devices. So here is the IEC 61850, and as you can see here, we have different definitions. So we use the the logical node to visualize the current and the voltage measurement and circuit breaker position and so on. So in the terms of hierarchy of the IEC 61850, we can conclude we can conclude and we can summarize this logical devices and logical nodes, data objects and data attributes. And let me explain what's the difference between each of them, just to give you a clear overview about the terms. So the logical device represented in LED, this can represent a functional unit of an IED or intelligent electronic device. So it can be the protection relay. So the main function of this logical device is to group multiple logical nodes into one functional. So as an example, the logical device representing a distance protection function or the overcurrent protection function. On the other hand, the logical node represented in LN, the logical node represents a specific function like protection, measurement, and control. So it contains data object and reflects a real life function. So it has a standard abbreviated name. So for example, if we have PTOC, it stands for the overcurrent protection. So also another example, it can be MMXU, which stands for the measurement of electrical quantities for voltage and current. The third term called the data object, as you can see from our screen. The data object, it represents a piece of information related to a functional logical node. So it groups a specific data like the settings, the status for a logical node. In example, if we have the PTOC, we can have a data object called STR. STR here, or start here, indicates whether the overcurrent protection has started. Okay, in the MMXU for measurement logical node, also you can have the phase current for the current measurement for phase A, phase B, for phase C, and so on. Okay, but this data object contains multiple data attributes. Okay, so the data attributes, it's a piece of data within a data object. What is the meaning of data attributes? It defines the actual data values in Boolean, integer, float, and so on. Okay, so for example, if we have the PTOC for the overcurrent protection .str and stval, so the stval here is the actual Boolean value indicating the start condition. Okay, and also in the measurement logical node, which is called MMXU, you can have the phase A cval.mag, which can represent the magnitude of the phase A current. So in summary, we have we have the logical devices LED, we have the logical node LN, such as the PTOC. Also, we have data objects such as STR for the starting overcurrent detection. We have data attribute for the value of the starting value and quality and timestamp and so on. So here is the services using the sampled values and goose message, and also the client server services for the control, configuration, supervision, and SCADA systems. And here is how you can map this logical nodes, logical devices, and data object, data attributes to have the structure of the IEC 61850 using the client server protocol in the SCADA systems, or using the goose and sampled values protocol, communication protocol for using the Ethernet in the digital substation or the hybrid substation. Thank you.